So let's talk about time-dependent phenomena. As I mentioned previously, if H, the Hamiltonian, do not depend on time, it is quite easy to separate the Schrödinger equation and to find orthogonal set of solutions. However, if H depends explicitly on time, it is not easy. Actually, it is not possible to get such a decomposition. And so we have to solve a partial differential equation. So this is one of the problems with dealing with this kind of models. And in order to give an example, I would take the parametric oscillator, which is perhaps the most well-known time-dependent exactly solvable model. And well, this Hamiltonian is just an oscillator Hamiltonian whose frequency depends explicitly on the time. If you remember yesterday talk of Marco, he was discussing this say Hamiltonian as well, differential equation like this yesterday. So this is we will use a similar approach, but in this case to solve this Hamiltonian. So there is even if we cannot separate a eigenvalue equation for the Hamiltonian, it is possible to exploit other properties of this Hamiltonian. And it was noticed by Lewis and Riesenfeld that if we compute a constant of motion, I, let's say I, which satisfies this condition. No, well, this is an I, sorry. So this is the Heisenberg equation. So if this quantity is zero, if we find an I such that this is zero, it can be shown that it means an eigenvalue equation like this. And so instead of solving the eigenvalue equation for H, we have to solve an eigenvalue equation for I, the constant of motion or invariant. I will use both terms interchangeably. So next, well, we have the eigenfunctions of the constant of motion, but what about the solution of the Schrödinger equation? Well, it turns out that the solutions of the Schrödinger equation are given by this relation. So we can map the eigenfunctions of the invariant to solution of the Schrödinger equation just by adding a complex time-dependent phase, which is computed from this relation. In this way, this new psi solution to the Schrödinger equation. So you can see here that we have mainly three problems. We have H, the Hamiltonian. So first, we have to find the constant of motion, which is not always easy. In most cases, it's even impossible. And secondly, when we have the constant of motion, we have to solve the spectral problem, which if the invariant is difficult enough to get, the spectral problem is another problem. And finally, we need to find these phases, and these phases are not are also difficult to compute with. So this is one of the problems of why time-dependent phenomena in quantum mechanics becomes so complex. So in this talk, I will discuss how to generate new new models, new time-dependent models, just by exploiting all the properties of one stationary system. In this case, just keep in mind, we need these three quantities: I, the eigenfunctions, and the phase. I will show you how to get all this information just by using simple geometrical transformations. So yeah, well, I would like to remark that there is another approach introduced by Gross and Samsonov, in which they use a factorization method similar to the stationary one, in which we can generate new time-dependent models from either time-dependent or stationary ones. But this method has some flaws, and mostly is these intertwining relations. These intertwining relations are such that they not ensure the orthogonality of the new set of solutions. I mean, most of you may ask, well, what is the problem about the orthogonality? Indeed, there's no problem, but it is better to have an orthogonal basis to work with. It is much difficult to work if the eigenfunctions are not orthogonal. So this is one problem. In the stationary case, the new models are orthogonal if the former ones are also orthogonal. It's a property that it is inherited by the factorization method. And in this case, it cannot be taken by granted. So this is a problem, but even though I will not explain the details of this, but I will just show you what kind of potentials we can get. In this paper, we reported an oscillator, a time-dependent deformed oscillator, whose solutions are like this. I will discuss this potential in a minute in another approach which is more suitable. So the new kind of potentials that we get are like this. So you can see that is basically a harmonic oscillator potential whose deformation is changing in time. I mean, this is the time evolution. And this is the first three solutions which are obtained by the same method. You can see here that the wave functions, well, the probability distribution, sorry, they don't have a well-defined number of zeros. Actually, the zeros disappears and appears periodically, mostly because the potential is periodic. But there is a problem because if you do all the math, you can check that those solutions are not orthogonal. So if we want to make linear superposition with this, well, it will be a huge problem. So given all these problems, well, I decided to explore another techniques, and one nice technique, and actually it's simple, elegant, and it gives all the information, is given by the point transformations. So this is the main topic of this talk, point transformation. So the main idea is the following. Well, point transformations in general is a method in which you can take a given partial or simple differential equation. It can be linear or nonlinear. Usually mathematicians use to map nonlinear differential equations into linear differential equations because, of course, linear differential equations are easier to solve. So once you solve the linear equation, you use the point transformation and go back to the nonlinear, and you can get the solutions on the nonlinear. That's the point of the point transformation. So in this case, I'm using an unrestricted class of point transformation, which is the form preserving, which means that I depart from a given differential equation of a given order. In this case, it's a second order in space and one order in time, and I will map it into another partial differential equation in second order in position and first order in time. This is the point, the form preserving, point transformation. In this case, y is this partial coordinate for the initial system, tau is the time, and psi bar are the solutions of the Schrödinger equation. So I will consider another partial differential equation like this, where x is the position for this new model, t is the time for the new model, and b is the new potential which I have to compute. And psi are the solutions of this new Schrödinger equation. In the first case, if you remember, the observable y, well, or the position observable is do not depend on time. So y and t here are not related. They are independent each other. And the same holds here, x and t. So these two quantities are independent each other. However, we can exploit another property. We can relate y with x and t with t and x, in such a way that x and t are not related. So this is the main point. This is the main idea behind all this technique, and all this information again is basically coded in these relations like this. In order to remark that point transformation are even more rich and they have more properties, and it can be generalized in several other ways. But here, for instance, I can add here a dependence on the wave function, and here as well, like I did here. But the problem is, if I do so, I will get nonlinear equations. So for the time being, I don't want to deal with nonlinear equations. I just want linear for the time being. So I will restrict these transformations like this, and this is the most important. Because if you can see here, if I find this relation, I can connect the solutions of the new Schrödinger equation with the previous one, and vice versa. I can go back and forth. So, well, yeah, so this is the main idea. Well, by introducing this into the first equation and doing a little bit of math, it's not easy to get this final result. And from here, you can see that this is the double derivative. From this relation, you can find a connection between the partial derivatives of psi with respect to x with those derivatives of psi bar with respect to y and tau. So from here, we have to impose some conditions to remove nonlinear terms. For instance, here, I will get a double derivative in time. Well, I don't need double derivatives on time because the Schrödinger equation doesn't have it. Secondly, here I will have I will get a nonlinear term from here. You can see this is the partial derivative with respect to x squared. So, but I don't want nonlinear terms. So I will fix this k in such a way that this quantity is 0, and also this quantity goes to 0. After doing all the math and all the calculations, I will get relations, these two new constraints. K is basically linear in psi with this new function to be determined, and tau is a function that depends only on time. And in the end, I get this partial differential equation. You can see here that this is almost the Schrödinger equation I wanted. So the new potential here, B2x, is given by all of this. So in order to simplify further, I have to impose any additional conditions. For instance, in the Schrödinger equation, this term is 1, because well, this is 1 over 2m, but I'm absorbing all the constants in the variables. So this term is basically 1. So this is another constraint. This is to 1. I don't want linear derivatives in x. I can include it if I want it, but for the time being, I don't want to include linear terms on the momentum. So I fix this to 0, and so on. So by doing that, I get a more simplified expression. The connection between the transformation is just given by this. The time is related by this, and the wave functions are given by this. So notice that the new solutions are basically the former ones, reparameterized by these y and tau functions, but also we had to add this function which depends on time and these local phases. So these local phases are important because well, they depend on x and also on t, sorry. So this is y, and the new potential just takes this form. And this is one of the more remarkable properties of these point transformations, and it is the preservation of the inner product. As I mentioned previously in the other approach, the orthogonality it was not granted, even if the former system has a set of orthogonal solutions. However, here, the point transformation just gives me that, well, the inner product will be preserved after the point transformation has been performed. So if I have an initial orthogonal set of solutions, I will get a new orthogonal set of solutions. As simple as that. So this is quite a remarkable property for this method. So what about the constants of motion I talked about recently? Well, if you remember, the point transformation was used to deform the complete Schrödinger equation, not the eigenvalue equation. So let's think of the following. Well, first, the point transformation has another property, which is preservation of first integral, which means that if we have a constant of motion in the former system, such a constant of motion will also be a constant of motion for the new generated system. This is quite remarkable because we can exploit this property to get more information. Actually, this property is widely exploited in nonlinear system to find constant of motion whenever it's difficult. So in this case, let's think about the former system. What happens with the power from a stationary system? From a stationary system, Hamiltonian, which not depends on time, what is the first integral or constant of motion we can think of? Is the Hamiltonian itself, of course. So we can take this Hamiltonian constant of motion and we can map it, and we are sure that the new mapped quantity will be a constant of motion on the new system because this property of the point transformation. So that's what we are doing here. I apply the point transformation just to the Hamiltonian, not the Schrödinger equation, just the Hamiltonian. And the initial Hamiltonian is stationary. So by doing all the math, we get this. And this is the new constant of motion of the system. Well, this is in coordinate representation, or you can take a look here in terms of operators. So in general, this is the most general way to get the constant of motion. And well, if we have the constant of motion, remember we have to get also the eigenfunctions. Well, the eigenfunctions are simply given by this. I will explain a bit later a bit more about this fact. Sorry. So this is the result. So just recall, we needed the invariant operator, a set of orthogonal solutions, and the time-dependent phase. We already have the set of orthogonal solutions because the preservation of the inner product, and we already have the invariant operator, constant of motion, and its spectral product. So so here is basically a scheme which summarizes this technique. Basically, if we apply the point transformation, we get another system. That's it. But we can exploit even further the technique to get this, to extract the constant of motion, the spectral problem, yeah, and the time-dependent phase, which the phase I was talking previously is just the time. The map time is the time-dependent phase we need. So, in order to test this, let's use the harmonic oscillator. If we depart from here to here, well, from here we apply all the technique, and in the end, the new potential takes this form, where the sigma functions are solution of the Markov equation. Yesterday, Marcos talked about this, so I will not talk any further about this. The gamma is the solution, and eta is it's just a complex phase. So you can see here that we already have a way to compute sigma. We only need to solve this. And the solutions of the parametric, and the new potential is the parametric oscillator. So the new solutions are just given by this. These are the local phases. This is what basically the time-dependent normalization. Well, it acts like a normalization constant, and this is the invariant operator. And in the special case that gamma and f, the external force, is 0, we recover the result of Lewis and Rice effect. In this way, we didn't need to use any ansatz or any other treat. It's just mapping properties, just exploring properties of the point transformation. So it's as simple as that. And well, just finally, just to discuss before the, we show new time-dependent potentials. And basically, the idea is quite simple. In the previous scheme, I showed you that if we depart from the Schrödinger equation and apply the point transformation, we can get these mappings. However, if we apply in the middle the Roost transformation or the factorization method, my first part of the top, we can get even more rich potential, and that's what I'm doing here. I depart from the oscillator, I apply the factorization method, I get this new time-dependent potential, which looks like this, and on the other hand, I get the new invariant operator. And take a look at the invariant operator. It has this function f, which is given by this, and if I would impose an ansatz, it would be difficult to figure out this kind of term. But the point transformation I just using the mapping of the constant of motion, and this arises naturally. So well, this is the transformation, and this is a summary in the spectral properties. Here I'm adding a level in the Hamiltonian, and by using the point transformation, I'm not adding level to the Hamiltonian of the new model. I add levels to the invariant operator, or the constant of motion of the new system. So that's the main difference, remember, because the Hamiltonian by itself do not satisfy an eigenvalue problem. So all the spectral properties are in the invariant operator. So this is an example of how the potential looks like. It's a periodic potential. We can give another properties to get non-periodic potentials, but well, this is just one example. These are the solutions. Well, probably they cannot be seen, but if you take a zoom around here, you can check that at any time the eigenfunctions have a well-defined number of zeros, and although they are orthogonal just by the properties of the preservation of the inner product. So well, this is the main result. And if we, well, in this case, I'm using the frequency, the time-dependent frequency equal to the constant. So even though the frequency is a constant, the new potential is time-dependent, and the time dependence is given by this additional term. Even if this is 0 and this is constant, this term depends on time. So it's quite interesting how we get a time-dependent model just from the conventional oscillator. And the last one, just to finish my talk, is, well, what happens if gamma is a function of time? So here we have a hyperbolic tangent. You can see here like a function, like a constant, which takes values omega 1 minus omega 2 at given times, and then changes smoothly to omega 1 plus omega 2. So it can be seen like a step function, but it's a smooth function that regularizes the step function. Well, the solutions for the sigma are, well, basically hypergeometric to F1, and the new potentials looks like this. So, well, and these are the probability distribution. Again, you can check the zeros, the orthogonality, and all the properties. So before concluding, I want to give some additional comments. For instance, this I'm dealing in this case just with the emission of self-adjoint Hamiltonians. But this technique can be explored even further. It can be applied to non-Hermitian models and some other systems. Quite recently, but with Oscar, we have been exploring the PV position-dependent mask cases, time-dependent mask cases, and a lot of other systems can be exploited by this transformation. And more remarkably, I didn't have it here, but even non-linear Schrödinger equations can be explored by this technique, but that's something that we are still working in. So, well, this is all I have for today, so if you have any questions, please.
Questions? Remarks?
Have you checked if you have a richer structure, if you have if you are another dimension to the problem?
Oh, yeah, that's something I have been exploring even. By adding one additional dimension, the math gets more complicated, even in the stationary case. And for the time being, I couldn't tell you what is the most general transformation, but you can, of course, you can, because this technique is applied for any partial differential equation. If you add another degree of freedom, it's just another variable for the partial differential equation. So yeah, you can apply it, but it's not easy. That's the only problem.
Yeah, well, just a comment that there are some works that they study the conformal mapping, and in those situations they are able to change the domain of definition of the potential. Mm-hmm. That could be also interesting.
Yeah, actually here, yeah, it can be done as well. I didn't discuss this, but this is only one of the models. We have other models with time-dependent boundaries, and actually in that case we're moving the domain, as you mentioned. However, in this case, it's time-dependent, the domain. And physically speaking, I'm not sure what it means, so that's why I didn't include it in this stuff. But yeah, it can be done. For the two-dimensional case, I forgot to mention. If the initial system is separable in like the harmonic two-dimensional harmonic oscillator, it's easy to apply because you only need to apply the point transformation separately. However, if you want to consider a non-separable, that's the tricky case. So, yeah.
More questions? Okay, there was